Hey guys. So yesterday we finished up exponential functions. So now we're going to have a look at logarithmic functions. So a lot of times when people hear logarithm, they make some sort of joke about playing a beat on a tree or something like that. But really, we have to figure out what the heck is a logarithm. So a logarithm is an inverse function of an exponential function. So remember, when we have inverse functions, x and y switches. So that's an important thing to remember when we go through and we graph them, is that x and y switches. One of the things that's also really helpful is to know that these two equations are equivalent. That's what that little tilde in the middle means. So that said log base b of a equals x is the same thing as b to the x equals a. So if you look at your calculator, you're going to see something that says just plain old log. It doesn't have any sort of base written there. If there's no base written there, that's going to be base 10. It's called the common base, or the common log is base 10. So let's go ahead and write them in alternating forms so that way we can get used to looking at the relationship between exponentials and logarithmic functions. So we want to write all of these first two guys in exponential form. So the first one, hang on. So one little thing that I think is helpful is that you can kind of think of this as a little bit of a loop. You start with your base, you pick up your exponent, and then it's equal to a. So it makes a little loop to get from your log to your exponential. So when we have log base 4 of x equals 3, 4 is my base. I come in around, pick up 3 for my exponent, and then it will be equal to x. So 4 was my base. We came around and picked up 3 for our exponent, and then it's equal to x. So that's how we would write that equation in exponential form. Same thing over here on this next guy. My base is 6. I'm going to come around and pick up my exponent x, and then I set it equal to 36. So I have my base is 6, come around and pick up my exponent is x, equals 36. All right. So what I think is helpful when I go and I write things in logarithmic form is I always have to remember that logs were made so that way we could figure out what powers. So like when you have like 2 to the something equals 8, what's x equal to? And or 2 to the x equals 8, what's x equal to? And you say x is equal to 3. Going through and solving for that when you don't know what that number is, we had to use logarithms. So the entire reason for these were to find the value of exponents. So I know that my answer to a logarithm, or what that logarithm is going to be equal to, is going to be my exponent. And then whatever this guy is he's the base. This guy that we're equal to, he's the one that's kind of floating around inside in the middle, inside of my log. So for 3 to the x power equals 27, I'm going to have log. The base of this guy is 3, so I'm going to have log base 3. At the very end, I want that to be equal to x because that's my exponent. And then my 27 is just going to go right there. Over here on B, it switched around, but it's still the same idea. When we write this out, we want to start with log. And then my base on this one is x. After all of that, when I have equal to my exponent always goes on the other side of the equal sign. And then to fill it in right here, I have a 39. I know it feels like I'm jumping around a little bit, and you might be able to go through and write those out just fine, but I have to think through it a little bit, and so I have to think through it that way. So, all right, let's go ahead and graph and analyze log base 2 of x. So I think one thing that would be really, really helpful is rewrite log base 2 of x in an exponential form, so that way it's a little bit easier to solve. Okay, so if I were to rewrite this, I would have f of x equals, my base is 2, and then that would end up being to the y power, right? Equals x. Ooh, let's write this a little bit differently. Hang on, let me write this bigger. So, we have the 2. If we kind of think about this being equal to y over here, 2's exponent is y, and then that will be equal to x. So if we rewrite this function in exponent or exponential form, 2 to the y equals x would be the equivalent exponential form. So if we want to use that, plugging in something for y and then getting the x value back is going to be a lot easier than having an x value and then trying to go back and plug it in to find y. So my advice for these is definitely to plug in for y and then solve for x. That will make life a lot easier. Plug in for y, solve for x. So our values for y, I'm going to use the usual stuff that I plug in for my independent variable. And remember, right now you're like, I'm plugging in for y, this feels weird, it should be switched around. Well, remember, logs are the inverse functions of exponentials. So x and y switches. So this time, instead of plugging stuff in for x and getting y, now we're still plugging stuff in for y and getting x. So for this independent variable this time, I'm going to plug in -3, -2. Oh, that's really hard to see. Let me pick a darker color. There we go. -3, -2, -1, 0, 1, 2, 3. All right. So let's go through. If I take 2 to the -3rd power, remember that negative makes it put it down on the bottom, so now we have 1 over 2 cubed, so that's an 1/8. Two to the -2nd power, so that negative exponent puts it on the bottom. So now we have 1 over 2 squared. 2 squared is 4, so we have a 4th right here. Plug in -1, negative exponent takes it to the bottom. So now I have 1 over 2 to the 1st, or just a half. Anything to the 0 power is 1. 2 to the 1st is 2. 2 squared is 4. 2 cubed is 8. So we did the exact same thing we did with our exponential functions, except this time we switched our x and our y, which is exactly what it means to be inverse functions, right? We switch our x and our y. So let's go ahead and graph all of these. Make sure that you are, when you're graphing these, that you completely forget about what you were just doing when you were plugging them in. Remember, These are your x values right here. These are your y values right here. So I'm going to go over 1/8 and then down 3. Don't switch it up. Okay, let's start graphing. Over 1/8 down 3. Over 1/4 down 2. Over 1/2 down 1. Over 1 up 0. Over 2 up 1. Over 4 up 2. And then over 8 up 3. So it's going to look like this. So, let's pretend that has some more curve on it right there. There we go. Okay. Pretend like it has curve. All right. So, on this right now, you might be thinking, oh, that looks a lot like an exponential function. Yeah, it is. It's going to be a reflection of the exponential function, right? Since logarithms and exponential functions are inverses of each other, then their graphs are reflected over y equals x. So a lot of the things that are true for exponential functions will be true for logarithmic functions, just switched with their x and their y values. So you might remember that with exponential functions, there was an asymptote at y equals 0. Well, like I just said, x and y are going to switch. So now I have an asymptote at x equals 0. And you might remember that exponential functions, their domain was from negative infinity to positive infinity. Well, that's not the case for our domain here, but since our x's and our y's switched, my domain of my exponential function is the range of my logarithmic function. So right here we can even see that line, that part of my curve says it's going down to negative infinity. And then this is growing, although small, it's still getting larger and larger and larger. So my range is going to be from negative infinity to positive infinity, just like my domain of my exponential function. The range of my exponential function, remember, was just from 0 to infinity, since we had that asymptote right there. Well, since our x's and our y's switch, now when we're thinking about our domain, it's the same idea as our exponential range. So my x values don't start until I hit right here at 0. And since I have an asymptote there, I don't actually touch at 0, so I need to have a parenthesis on that. And then I have x values all the way on out to infinity. My x-intercept goes through right here. You might remember that the y-intercept on those exponential functions were at 0, 1. Well, if we switch our x and our y, our x-intercept here is at 1, 0. Sorry, my cat's playing with a toy over there, so he's making some noise. He's just being a chubby kitten and being happy. Okay, moving on. Now let's talk about that same sort of graph, but this time we're going to graph log base 1/2 of x. So if we were to rewrite this in exponential form, so like if this was equal to y, if we wrote that in exponential form, I would have 1/2 to the y power equals x. So like we talked about just on this problem before this, it's going to be a lot easier to plug things in for y and get a value for x than vice versa. So we're going to go through and plug things in for y and then solve for x. So we've got -3, -2, -1, 0, 1, 2, 3. All right. So if I take 1/2 to the -3rd power, so that negative on my exponent takes that 2 to the -3rd power, brings it up to the top, and makes it 2 to the +3rd power. So 2 cubed is just 8. 1/2 to the -2nd, so that 2 is in my denominator with a -2 on him for an exponent. He moves to the top and my exponent becomes positive, so 2 squared is 4 for that guy. When we plug in -1, so 2 is down here in my denominator with a -1 on him, so he moves up to the top and my exponent becomes +1, so he's just 2. Anything to the 0 power is 1. 1/2 to the first is a half. 1/2 squared is a fourth. 1/2 cubed is an eighth. So now we'll go through and graph all of these. This one is going to feel even weirder because your x values aren't in order this time. So it's going to feel like you're going all sorts of backwards. So if you need to go from bottom to top in your list, or you just need to pay really good attention, I don't know, we can figure it out. I'm going to go from bottom to top. So 1/8, 3, 1/4, 2, 1/2, 1. Okay, I'm going to have 1, 0, and then we have 2, -1, 4, -2, and 8, -3. All right, so if we connect those guys. Ooh, that's not a very good one. Let me try it again. Oh man, that's a good log. Doesn't that look beautiful? Okay. Once again, we have this asymptote chilling over here at x equals 0. Our domain, so our x values don't start until 0. Since there's an asymptote there, we don't actually touch at 0. So I'm going to have a parenthesis there, 0. And then my x values go off to infinity. And then my range, even though it's starting to slope off a little bit, this function is always going to keep decreasing forever and ever and ever. So my y values are going to go from -infinity until +infinity. And then my x-intercept happens right here at 1, 0. So now we want to graph different functions using transformations of that original function that we graphed earlier. So first we want to graph log base 2 of x plus 3. So I went ahead and pasted in the graph that we found for log base 2 of x. And then we have to think about what happens with that plus 3. So remember, if it's in there inside with the x, that means it's going to move it horizontally. And anything that's inside there with your x is going to be opposite of what you think it's actually going to be. So if it says x plus 3, you're like, hey, we're going to the right. No, 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 you're going to the left. So we're going to shift everything to the left 3 units. So first of all, our asymptote has to get shifted left 3 units. So now instead of being over here at 0, we're going to shift over here and be at negative 3. And then I shift some of the easier to shift points first. So like I have that point at 1, 0. So when I shift that over 3, now I'll be at negative 2, 0. I had a point at 2, 1, so now I'll be at negative 1, 1. I was at 8, 3, so now I'll be at 5, 3. There we go. Okay, and then I can go through these. Okay, let's see. All right. There we go. Okay, so let's have a conversation about what changed here. So our domain, the x values definitely changed, right? Now we have some x values over here in our third and our second and our third quadrants. So my y values, or I'm sorry, my x values now start at negative 3. So I'm going to have a parenthesis, negative 3, and then I have x values all the way out until infinity. My range is still negative infinity to positive infinity. And my asymptote, like we said, it was at 0, and then it got shifted over. So it got shifted over to be at x equals negative 3. Our x-intercept got shifted as well. So it was at negative 1, and then it got, or I'm sorry, at positive 1, and then got shifted left 3. So now it's at negative 2. So my x-intercept is going to be at negative 2, 0. What do you think, puppy? Yeah? You want your math? You want your math? Yeah. Okay, let's look at another one. This time, we're going to take our log base 2 graph, but now we have a plus 2 on the end without any parentheses. So since there's not any parentheses, there's nothing to group that 2 with my x. So that means it's going to be dealing with my y's, so it's going to be shifting me up and down, so vertically. Nothing weird happens here, so I'm going to be shifting up 2. So I'm going to take each of these points and shift everything up 2. So let's see. Is that 1/8? 1/8. A fourth. Oops. And then 1, 2. There we go. So when we shifted up and down, my asymptote didn't change at all. I still have my asymptote right there at x equals 0. So since my asymptote didn't change from x equals 0, that means my domain doesn't change either. My x values still start at 0, so I'll have parentheses, 0 to infinity, close parentheses. My range I still have as negative infinity to positive infinity. And I got shifted up 2, right? So what was at negative 2 is now up here at 0. So the point that was right here at negative 2 was, or at my y equals negative 2 was 1/4. So my x-intercept, whoopsies, is actually going to be at 1/4, 0. All right, so these functions look a little bit strange. So when we talk about end behavior, we have to talk about it a little bit differently than what we looked at for a lot of other functions, polynomial functions, things like that. I don't think I actually mentioned this in the last video. Log functions, exponential functions, things like that, trig functions, those are called transcendental functions. They're called that because they transcend algebra. So you can't write it as a polynomial or anything like that. It has kind of different rules than polynomials tend to. So if you've ever wondered, what does it mean to be a transcendental function? It just transcends algebra. We have to do something else for it. So it's not a polynomial. Anyways, so end behavior. So we're going to talk about the end behavior of logarithmic functions, but this also applies to any other function that has some sort of restricted domain, that your domain is not from negative infinity to positive infinity. Because what happens if x doesn't approach negative infinity, or if x doesn't approach positive infinity? Do you just not do that end? Do you only have one end behavior? Do you not have both ends? How does that work? So, like I just said a second ago, we want to show what happens at both ends of the graph. So that means we have to have two things describing our end behavior. Remember, the end behavior was the limit as x approaches whatever, blah, blah, blah. We usually have as x approaches positive infinity, and then we have another one where x approaches negative infinity. Well, as we just saw in those graphs a second ago, x doesn't always approach negative infinity. And if this reflects over, it wouldn't approach positive infinity. So sometimes you're going to have issues like that with your graph. And so what do you do in those situations? So you want to show what x actually does approach. So we want to look at the asymptote there. So it's going to look a little bit strange, but we're going to go ahead and practice finding the end behavior of the four functions that we graphed today. So the first one we're going to do is the log base 2 of x. So that was our purple function right here. So let's go ahead and do the easy one first. So we know that x does keep going out in that direction forever and ever and ever. So that means that x approaches infinity. So when I start to write out my end behavior, I will have the limit as that function, f of x, of that function, as x approaches positive infinity equals. So remember, that function looked like this. As x got bigger, y got bigger and bigger and bigger. So as x approaches positive infinity, so does my function, so that will be equal to positive infinity. In IB or in other countries, when we talk about as this approaches infinity, or as x approaches infinity, they say x tends to infinity, then the function tends to infinity as well. It's just a different word to use. We say approach, a lot of times in the UK they say tends. So let's go back and look real quick at this graph again. So x doesn't approach, negative infinity on this side, right? The farthest that x goes over on its left side is over here at 0. So x is approaching 0 over here. We know that x doesn't actually touch 0 because there's an asymptote there, but I know that x is getting closer and closer and closer to 0 there. So with my end behavior, that means that I'm going to have the limit of f of x as x approaches 0. So x approaches 0 from just one side, right? So x approaches 0 from the right side, right? Okay, so since it's coming from the right side, and the right is on the positive part of our graph, it's going to have a little plus up in the corner. You're not going to have to worry about this too much until calculus, but I thought I might just show it to you. So yeah, it has a little plus as a superscript. Okay, so as x was approaching 0 over on this side, it was getting closer and closer and closer, and then my y values just kept getting smaller and smaller, right? They kept going towards negative infinity, so that will be equal to negative infinity. Okay, now we'll look at the end behavior for the log base 1/2 of x. So that was my blue graph right here. Okay, so in this one, once again, x does approach positive infinity. Since we're getting smaller and smaller, my y's are going down. That means that my limit is going to be equal to negative infinity. So let's write that out. My limit as x approaches infinity of this function. So since as x got bigger, y got really, really, really small, really negative, that means it's going to go to negative infinity. Now we have to look at the other side of the graph. Now, what is x approaching? So if we look back at this graph, over on my left side of the graph, x is approaching 0. And as x approaches 0, my y values get bigger and bigger and bigger and bigger. So the limit as x approaches 0 from the right, so I have a little plus sign right there, of f of x equals, and since we said that y was getting bigger and bigger and bigger and bigger as x was getting closer to 0, that's going to go to infinity. So the next ones are where we'll see a little bit of change. So on this guy, we had to shift our graph over 3, right? So still, we can even take a look at the graph if we'd like to. There he is. So still, x is approaching positive infinity, and my y's are still approaching positive infinity. So that first part won't change. The limit as x approaches positive infinity of f of x equals positive infinity. And now when we look at that left side of our graph, over here, instead of x approaching 0, now I'm over here approaching negative 3 since I was shifted over. So now I'm approaching negative 3. So my limit as x approaches negative 3 of f of x. And remember, the graph was going down at that point. So since the graph was going down at that asymptote, my y's are going to negative infinity. All right, so now we're going to look at log base 2 of x plus 2. So if we look back at this, my graph got shifted up, but nothing with the end behavior really changed. As x goes to infinity, y still goes to infinity. And then my asymptote didn't change, so x still approaches 0. And as x approaches 0, y still approaches negative infinity. So we have the limit as x approaches infinity of f of x. Since my y's got bigger, that's equal to infinity. The limit as x approaches 0 from the right of f of x equals negative infinity, since it was going down. All right, guys, so I hope this was helpful. You can expect some logarithm practice tomorrow. I'm not really sure how it's going to look or if I'll really be able to check your answers in a very easy to do way. We'll check it out and try a few things and see how it works. I miss you guys a lot though, so I hope you're doing well and staying home. So see you later.